Okay, welcome to Lecture 5. Through Lecture 5, we'll talk about the principles of HPLC, which stands for High Performance Liquid Chromatography Methods, as well as the electrophoresis method that will help you to separate out protein molecules. Okay, first, High Performance Liquid Chromatography, which stands for HPLC. So the chromatography methods we talked about in the previous lecture are mostly used to purify your target protein. So we normally group them or call them as FPLC, fast protein liquid chromatography methods, which are primarily used to purify your target molecule. However, HPLC is also used a lot, especially for the purpose of qualifying and quantifying your target protein molecule. Instead of purifying it, you're using HPLC to quantify and qualify. So HPLC is used a lot in your QC analytical method in that area. Okay, so regardless of HPLC or PLC, the principle of separation is the same. You have the column, and then resin packed with the resin, and then you have the mobile phage. The buffer is running through your column, and then your sample is loaded to the column, and you will get the fractions coming out off of your column. The same principle. Okay. But HPLC, as it says, high performance or high pressure, you will apply the high pressure to the column. So, which means through a high pressure or high flow through, high flow rate. You can get your fraction done within a very small amount of time, and the resolution will be much greater. Okay, so those are the, I guess, good advantage of running an SPLC. So the sample typically is analyzed in very small volume to a stream of mobile phage, and is retarded by the specific chemical or chemical interaction with the stationary phage. Again, it's the principle of column chromatography methods. Okay, and then retardation of your molecules from your column is basically how you will be able to separate out your molecules. So where do you use this? Like I said, mostly it's analytical purpose. That's where you use HPLC. So you're focused on obtaining an information about the sample compound, whatever that compound is in your sample, and then information about what it is, the identification, and how much do you have can be obtained through this HPLC analysis. Okay, and sometimes you could use it for preparatory, meaning you can purify your target molecule in a very small scale operation, but that's very rare. Okay, column size, typically HPLC columns are very small, and it has very thin diameter. So 10 millimeter is about 1 centimeter. That's a typical column diameter, very small column. So that's why it is normally used for analytical purpose. Okay, sometimes it's 4.6 milliliter diameter, about half of the 10 millimeter column. Okay, and it can withstand, as the name says, a lot of pressure, 6,000 pound per square inch pressure. So you can run your column very fast. Normally, your column is made up with the metal material. Column housing is the skid, and then the tubing as well. Normally, it's metal tubes. Okay, then we're going to talk about electrophoresis separation of protein. We already talked about it in the previous class a little bit. We're going to dig a little deeper in this class. So we already talked about SDS page, right? SDS is a sodium dodecyl sulfate. It's a detergent that will allow you to denature your proteins, and then not only it denatures your protein, it will also bind with your proteins. And since this SDS is negatively charged, you will have your protein uniformly negatively charged once you bind your proteins with SDS, right? And the page stands for 1 polyacrylamide gel electrophoresis. Normally it's a one-dimensional gel electrophoresis. You're going to separate out your proteins on that gel. Okay, So by doing so, you can get the information about the molecular size of your target protein or purity of your protein. Okay, because size you can get it by comparing against the size standard markers, right? And the purity, the more proteins you have, that means your protein is not pure. The less number of other proteins you have, that means your protein is pure. That's what it means, right? So this STS page, or just a page, is one of the high resolution purification method. What does that mean? High resolution, it can separate out your proteins very detailed. So only your protein can be separated out. So that's what high resolution means from other unwanted proteins. And then, yeah, you add a lot of STS, about 0.1% total volume is made up with STS in your gel and in your sample prep, right? And then when you denature your proteins with STS, not only you add STS, you also add something called a reducing agent. Reducing agent, remember, the beta-mercaptoethanol or dithiothiranitols are those reducing agents. They are added to what? To break up those disulfide bonds between two cysteines. Okay, so you can add this. You're adding this to reduce the disulfide bonds within your proteins. So your sample is denatured with STS loading dye. Normally loading dye has STS in it. You also need either beta-mercaptoethanol or DTT in your loading dye as well. Okay, and then the gel and the buffer also contains the STS in them. Okay, STS is an anionic detergent that binds with your proteins. Okay, I'll show you the structure of STS in a slide also. So your proteins are separated on your gel, and then small molecules will migrate faster towards the positive charge, while large molecules will migrate very slow. So that's the size-based separation that you will get on your gel. And then that page can be run without the presence of STS. When you do that, you describe that as non-denaturing gel electrophoresis. Non-denaturing gel electrophoresis, because your proteins are not denatured. So without the presence of STS, your proteins will have their own charges. Okay, so it's a non-denaturing gel. And typically, non-denaturing gel can be run on a column gel like this. Okay, and then you will have a gradient of, pH. Okay, by adding different molecules that have different charges, you can create a gradient, and then you'll add your sample and hook up the electric current with the gel. Then you will see your proteins are separated based on their charge difference. So you can separate out your proteins based on their charges, not based on the sizes. That's a non-denaturing gel, or another name for that is isoelectric focusing. Okay, so remember that term, isoelectric point. So that's the pH value where your protein will become what? Net neutral, no charged, right? So you create these pH gradient in your gel, and then your protein will migrate towards its isoelectric point. And once it's reached that neutral point, it's going to stay put, because it's neutral protein, it's not going to move anymore. So that's the separation it's happening on this non-denaturing gel, or isoelectric focusing. Okay. Once that isoelectric focusing is done, that column gel can be taken out of the container, and then column gel can be loaded on top of your slab gel, which is the STS page. Okay, and then if you connect the electric current, okay, then your protein will migrate from your column gel. It's going to migrate into the slab gel, but the slab gel has STS in them already. So you're going to see the binding of STS with your proteins when you do that. So the second gel, which is a slab gel, is STS page. So after finishing your isoelectric point, now you can do the STS page after that. So it's a continuous process. First step is isoelectric point, which is a charge-based separation of your proteins. And then second step is the SDS page, which is the size-based separation. So at the end, you may get a result like that. Okay, so these proteins are separated. Okay, first based on their charge, the pi difference. Okay, and then this side is based on their size. So these are small proteins. Okay, and then these may be, I don't know, the pi value of whatever that 8 or 9. Okay, so you can say two things about this protein. It's a small, and then it has the pi value of about 9 or 8. Okay, you can say, how about this one? This is large, fairly large, and this has the pi value of 10. Just two set of information you can get if you run this two-dimensional gel electrophoresis. Two-dimensional gel electrophoresis. What that means is, first dimension, it is the charge-based separation. Second dimension, it is the size-based separation. By combining those two results, you get two sets of information together about your protein. Okay, that's what two-dimensional gel electrophoresis is. So as I just explained, let's say you're comparing two cell types. Maybe one cell type is normal cells, the other cell type is maybe cancer cells. Okay, you want to see what different proteins do these cells have, right? Then you can isolate their cells, their proteins from these cells. Okay, and then you do the isoelectric focusing first, meaning separate out those proteins based on their charge first, right? And then after that, you do run those proteins, these column gels, on top of your SDS page, then do the size separation next. Okay, and then those results can be compared side by side. Okay, so if you see any different pattern between those two results, those differences may come from maybe difference in their protein profile. Maybe some proteins may be only found from cancer cells, some may be only found from normal cells. Okay, so it's a very high resolution protein separation technique. And that's what 2D electrophoresis is. Okay. Again, I told you the structure of the SDS. It looks like that. Okay, sodium dodecyl sulfate. So you have a high, long hydrocarbon chain, which is pretty much non-polar. Okay, no charge. But here, this SO minus head is what charged head. Okay, so this part is used to bind with the proteins. So you see the hydrophobic interactions in this part, and then this part will give you the negative charge. That's what SDS would do. And the beta-methylcaptoethanol dithiothyronitols are reducing agents that they break off the disulfide bond, as I told you. And then SDS page gel, it may come in as a continuous gel or discontinuous gel, depends on what gels you are using, okay, making or buying. So the main difference between the continuous and the discontinuous gel is if gel is made as a single gel, or if your gel is made as a stacking, meaning two gels together. For example, this is a discontinuous gel, so you have a stack of two separate gels together. Okay, you may be able to buy something like that. So the bottom part is considered the resolving gel, and the top part is considered as a stacking gel. So the main reason why you make this continuous gel is the stacking gel is a low percentage gel, and the bottom part is a higher percentage gel. So by having a little bit of this low percentage gel, you're going to have your proteins migrate through your gel more easily. Since this may be made up with only 3% acrylamide instead of maybe 12 or 10%, your proteins are well separated first here through the stacking gel, and then they will be separated further on your resolving gel. So it gives a better migration of your protein samples into the gel. That's the whole purpose of having the stacking gel. But these days, you rather use a continuous gel that is gradient formation. So we'll talk about that.